Sarah, the neat thing about this unit, you're going to notice it really parallels mathematically how gravity works. Electric force and gravitational force are both field forces, and so the underlying mathematics is going to look really similar. You're going to see, for example, that R's appear and R squareds appear in the same place in electrostatics equations that they appeared in their counterpart in gravitational field equations. But the weak part of this, the difficult part of this, is all of the equations start looking alike after a while, and it's really easy to mix them up. And all I can say is do the homework on time. You've heard this speech before, but do the homework on time. Do not try and cram this one in at the last minute. You'll find everything gets confused, and it's going to get all jumbled up. Trust me, I know what I'm talking about. We're going to start off with something that I hope you all know, but maybe not. Matter is made of atoms. Really? Yeah. And a standard atom has at its core a nucleus, and the nucleus is typically positively charged. And then it has in shells around it, this says orbits. We've kind of fallen away from using the term orbits because now that you know what an orbit is, gravity is what's pulling me in a circle, that's not what's going on here. So the whole notion of imagining electrons as little dots whizzing around a nucleus is not correct. So we say shells, but the electrons have a negative charge. When atoms bond together to form solids, these electrons, which is where most of the action happens, can be tightly bound to the atoms, especially in covalent solids like glass. Where the electrons are tightly bound, we call them insulators. They don't allow electrons to flow very easily or not at all. Or the electrons can be free to move around, especially in metals. These will be called conductors. In a conductor, each atom is happy to pass an electron from its valence shell to the next one, 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 to the next one. The three subatomic particles, protons, neutrons, and electrons, have a property. And we've given this property a name. We call it charge. Why do we call it charge? I'll explain where that comes from in a video that you'll see later. But this thing that we call charge is responsible for all of electricity and, it turns out, all of magnetism. Electricity and magnetism are not separate forces. They are part of one big force called electromagnetism. They're two sides of the same coin. Some basic facts about charge. There are two types of charge that we call... What are the two types of charge? Zach? Positive. Now, you know I tend to abbreviate. To me, that's a plus sign, and I'm looking for an equation to go with it. My abbreviation for the word positive is that, and my abbreviation for the word negative is that. That's my own made-up thing, and that's just because, Tato, as a math nerd, if I just see a minus, I go looking around for an equation somewhere. So if I'm writing the word in a sentence, positive or negative, you'll see me do that. You don't have to. You can use a plus or a minus. It's duik being duik. What are the units for charge? What is charge measured in? It's in the title. Coulombs. 1 coulomb is massive, huge. If you absorbed 1 coulomb all at once, you would die. And in fact, you would die probably in the stereotypical Hollywood electrocution style of death with sparks and melting and yuckiness. If you absorbed 100 coulombs all at once, probably there would be very little left of you but some ash. But it's all about, Chang, how fast you absorb the coulombs. This battery has about 2,500 coulombs in it. I'm perfectly safe because I'm not going to be absorbing it very, very quickly. Speaking of very, very quickly, or not so very, very quickly, I could, like, even though this battery has about 2,500 coulombs of charge, I could put it in my mouth and complete the circuit. I'm perfectly fine. I'm not going to be absorbing all that charge at once. You might notice if you ever put your tongue on a 9-volt battery, you're absorbing charge a little bit quicker. That's enough that you can actually feel it. I suspect right now, just holding the battery like this, my fingers are technically completing the circuit. There is probably some current flowing, but it's so small I can't feel it at all. it's going along the outside of my skin because your skin is actually a reasonably good insulator. I don't know. Charge is represented by the letter. We can't use c. That's taken for the speed of light. So what letter do we use for charge? Q. Q. Why Q? Actually, it makes perfect sense. We use the letter Q because of quantum. What? We're going to talk a little quantum physics here. We use the letter Q because charge is quantized, which means it comes in chunks, sort of like our money. What's the smallest coin denomination that we have, even though it's not in circulation anymore? The penny. We do not give you bills to 3 decimal places. We do not get a receipt to 4 decimal places. By definition, our monetary system does not allow for anything smaller than the penny. You automatically round off. By definition, the universe does not allow for anything smaller than an elementary charge, the elementary charge on an electron or a proton. Charge comes in chunks. It's quantized. That's the fancy word for comes in discrete chunks. It comes in quantities. It's where the root word of the word quantity comes from as well. So we use a Q for that idea, for that letter, for that variable. So we have the whole number of pennies in our monetary system. So $1 is how many pennies? 100. We would say it's 100 of our fundamental base unit. $5 is 500 pennies. A nickel is 5 pennies. It's 5 of something. That's why nickel, when you say the word nickel, you think 5, not 7. With respect to charge, the smallest unit of charge is called the elementary or fundamental charge, and it's on your formula sheet on that data section where you also have mass of the Earth and blah, blah. What's the elementary charge? Plus or minus 1.6 times 10 to the negative 19 coulombs. Positive, that's a proton. Negative, that's an electron. All other amounts of charges are a multiple of that. So if you want to, for example, figure out how many electrons or how many protons there are, we will later on actually do a calculation. We'll figure out how many electrons are stored in this battery. It's going to be probably a few trillion, a fair number of them. Any other charge is equal to the number of charges times the elementary charge. Now, I've fibbed to you a little bit. Some of you might know that since this was all defined and the elementary charge was defined back in the 1910s, we learned later on, once we started building particle accelerators, that if you smash protons together at crazy high speeds, they break. And you actually get things called quarks. And quarks actually have charges of plus or minus 1/3 of an elementary charge or plus or minus 2/3 of an elementary charge. And so, Gurjot, I've lied. In the quantum world, there is something smaller than the penny, but we're going to pretend it doesn't exist because it makes the math yucky. But if you want to do a YouTube search for what are quarks, and you'll find some good, interesting videos. You'll also see in physics, once again, we know how to name stuff. Anybody know the 6 quarks? What they're called? Up, down. Up, down, strange, charm. And some say top and bottom, some say truth and beauty. I like truth and beauty because that's much more poetic, but we know how to name stuff in physics. None of this endoplasmic reticulum garbage. God, biology. Well, hang on. I've been talking a little bit about quarks. We're going to pretend that they don't exist. Although they're cool. In this course, you're going to get a formula sheet. You already have it. So things that you do not need to memorize, although you might end up memorizing them because you're lazy. Probably by the end of this unit, you will have memorized the elementary charge. But also on your formula sheet, can you see where there is the mass of an electron? It's also in that data section. And the mass of a proton, it's also in that data section. I think, did I give you the mass of a neutron? You know why? We're never going to use them. They have no charge. They're interesting. By the way, the reason a neutron has no charge is the way it's made up It's a proton and an electron that have been smooshed together along with a couple of other obscure weird subatomic particles. But what is +1 plus -1 elementary charge? Okay. An atom walks into a bar and says to the bartender, "I've lost an electron." The bartender says to the atom, "Are you certain?" The atom says, "Yes, I'm positive." A neutron walks into a bar and says to the bartender, "How much for a drink?" The bartender says, "Oh, for you, no charge."
That's your
Okay. So what the data page does not do is explicitly list the charge of each particle, so you'll have to remember the following. You'll have to remember that an electron is negative. And so the charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. You'll have to remember, and I think you all know this from your science and chemistry knowledge, that a proton is positive. If I was a good teacher, I'd have a dumb way for you to remember that a proton is positive. If I was a better physics teacher, I'd have something stupid that you could easily remember that a proton is positive. I got nothing, so you have to come up with something on your own. 1.6 times 10 to the negative 19 coulombs. And a neutron, no charge. So, turn the page. This doesn't need to be memorized, but you might recall from your Science 10 when you looked at radioactivity and gamma rays and radiation that there was something called an alpha particle. The symbol for an alpha particle was a Greek letter alpha. And it's a helium nucleus, which means it had 2 protons, 2 neutrons, and no electrons. What's its charge? What's the charge on an alpha particle? How many electrons does it have? How many neutrons does it have? Who cares? No charge. How many protons does it have? So it has a charge of 2 times 1.6 times 10 to the negative 19 coulombs. And I can do that in my head. I know that 16 times 2 is 32, so I think 1.6 times 2 is going to be 3.2 times 10 to the negative 19. That elementary charge, by the way, you can see it's really small. 0.0000018 zeros and then a 1 and a 6. For a conductor, electrons flow freely and easily. For an insulator, the electrons can't flow, but the electron orbits or shells can shift slightly so that you get a higher grouping of negatives in one area, and by definition then you must have a smaller grouping of negatives, more positives, in the other area. We call this polarization. Even though the overall charge of the object is still neutral, we can shift the shells around enough to have one area more positive and one area less positive. So that's what polarization is. Charge is one of the 4 fundamental forces. The 4 fundamental forces are electromagnetism. That's the one we're looking at. Gravity, although there's debate. Einstein said that gravity isn't a force, it's a curvature of space-time. Then there's the strong force and the weak force. And the strong force and the weak force, one of them is involved in radioactivity, I can't remember which one, and one of them is involved in holding the nucleus together because all those protons in the nucleus are all positive and they would normally repel each other. What's holding them together? It's either the strong force or the weak force, I can't remember which one. Charges exert forces on each other. Here is what I hope you remember from Science 9. Like charges, blank. Unlike charges, blank. Like charges, repel. And then usually I say something like, much like when Patrick calls someone up for a date. Repel. It's always a basketball player, and you were late today. Unlike charges will attract. I could have said much like when Patrick calls, but I went with repel, because why not? If I was drawing the forces on these 2 charges right here, are they like or unlike? So we are going to have to figure out the direction of the forces ourselves by using like, repel, unlike attract. So I know that this negative is feeling a force up or north, and this negative is feeling a force down or south. Here we have opposite charges. They are being attracted to each other. One of the safest places to be during a lightning storm is inside a metal car. Why? Linnea. The lightning has just jumped 2 kilometers from the sky to get all the way to the car. I assure you it can jump that much further and reach the ground. The tires have nothing to do with it. And people always say, isn't the rubber tires? No, it is not. Nothing to do with it. You could lose the tires and you're just fine. Why? Car's metal. Why? Doesn't matter if you are. Yeah.
Because metal's a good conductor.
So? You ready? Like charges. Everybody, like charges. One more time. Like charges. So let's suppose this metal car absorbs 1 trillion charges. Positive or negative, because lightning can be both. They want to repel each other. They want to get as far away from each other as possible. What's the furthest they can get away from each other? On the outermost part of the metal. That's as far away as they can get from each other. Where are you sitting? Inside. You're fine. And it's counterintuitive, but the reason you're safe from lightning is because you're inside a metal shell. Nothing to do with the tires. It's because you're inside a metal shell. That's the safest place to be. Doesn't metal conduct electricity? Yeah, you're fine. First of all, the outer metal shell collects the charges. Like charges repel, so they gather on the outside of the metal. We have a little thought experiment, Ange. It says this. A negative rod is brought close to an insulating ball. The ball is first attracted and then repelled by the rod. Explain why this happens. What? Put your pencils down. Experiment? What's going on here? So we're going to do what we call a charge diagram. I'm going to zoom in. So initially, the little ball was neutral. I'll show that it was neutral by putting 2 pluses and 2 minuses. Really what I mean is there's like 200 trillion protons and 200 trillion electrons. It's even. And then the rod is negative. Now, just because it's negative doesn't mean there's no positives. There's some, but let's just make it really, 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 really negative. Okay? Like charges repel. Unlike charges. So if I bring this negative close to this ball, what happens at first is the negatives in the ball are repelled. They move to the right-hand side. The positives in the ball are attracted. They move to the left-hand side. And so what I have is, since the positives are closer to the negative rod, their force of attraction is stronger than the force of repulsion from these negatives over here. And so initially, this is why any neutral object will always be attracted to any charged object. This thing here, this process right there, we call polarization. But now, once they touch each other, like charges, come on people, like charges, unlike charges, the unlike charges, these negatives are going to jump across to be with these positives. So in the next diagram over here, we're going to have a situation where we still have some negatives. We still have those 2 negatives here. We still have those 2 positives, but we have extra negatives jumping. So now this styrofoam ball, instead of being neutral, is what charge? And what's the charge on the rod? Still, like charges. Some beautiful physics going on there in that tiny little, very simple demonstration. By the way, we suspect that this, what you just saw, is the origin of magicians' magic wands. Because if you don't know the science, that is witchcraft. I am making something move without touching it. Yes? And if you don't know the science, that, holy smokes, Batman, right? So we think this being able to charge a piece of plastic or amber is probably where the whole idea of a magician using a magic wand came from. Little nerd trivia for you there. Next one, I don't have a setup. We're going to do as a thought experiment. So, by the way, we call this is charging by conduction because we made contact. We physically transferred charge from one object to another. Does anybody remember from Science 9 the other way to charge an object without touching? Began with the letter I. Okay, you have induction and conduction. Science 9, the Science 9 textbook, I think is wrong because in science, I'm teaching it right now, and the Science 9 textbook says when you charge by induction, the charge is not permanent, it's temporary. I disagree. I'm going to show you a way to create permanent charge without ever touching. You ready? So two uncharged or neutral metal spheres are on fixed insulated supports. Maybe they're sitting on styrofoam, and they're touching. We're going to bring a negative rod in really close, and now I'm going to zoom in. So if I do that, like charges, where are all the negatives going to end up? On the left-hand sphere or on the right-hand sphere? Like charges. And so what's going to happen, originally the charges were spread out evenly, but what's going to happen, because they're touching, the negatives will flow there, and that will leave you with a bunch of positives there. Now, overall, both spheres, if you add them together, still neutral. And I have not touched the spheres with the rod. This is not conducting. Then what I do, with the rod still here, I grab the bottoms of the spheres, the styrofoam bases, and I separate them. Then I remove the rod, Stephen, from the picture. Stephen, what's the charge on the left-hand sphere? Negative or positive? Are you positive? Shut up. What's the charge on the right-hand sphere? I have permanently charged two objects. Did I actually transfer any charge from the rod? Textbook is wrong in Science 9. How many of you have an electric toothbrush? Okay, that charges through induction. You would not want metal contacts around all that wire that were bare and all that water. That's a bad system. If you look at the bottom, it's all plastic. How the heck do they transfer charge? You give engineers some time, in a few hours, they'll come up with clever ways that you can permanently transfer charge without actually conducting charge. Your phone pads, if you have a phone pad that charges your phone indirectly, that's an induction charger. Probably within 5 years, that will be the standard. You will no longer plug your phone in. You'll lay it down on a pad or some other system. I'm not going to specifically test you on those. I'll just use those terms so you should know them. Okay? A lot of this up until now is mostly setup. Here is your equation. The force between fixed charges, you saw when I took the plastic rod and brought it to the paper was attracted. There was clearly a force between them. It can be calculated with Coulomb's law. So we're going to use a capital F for force, lowercase e for electric, lowercase g for gravitational, lowercase another letter for magnetic, not M sadly, and it's calculated by lowercase k q1 q2 over r squared. Tato, what equation does that look an awful lot alike mathematically? Universal gravitation. Is there an r squared on the bottom? Yeah. Now, so what's this lowercase k? It behaves the same way big G behaved. Big G went there so that you ended up with an answer in newtons. It was your conversion factor. Lowercase k is the conversion factor, but it's a much, much nicer one. It's on your formula sheet. What is the lowercase k? 9 times 10 to the 9th. And then the units are probably newtons meters squared per Coulomb squared, or I don't care. A lot easier to type on your calculator than 6.67 scientific notation button, -11. If I need to type K, oh, it's just so much nicer because I already have my thumb over the 9 already. I hit 9 with my thumb. I hit my scientific notation button with my other finger, hit 9 with my thumb, bada bing. Much nicer. That's K. It's actually 8.9987. You know what? 9. Good enough. Q1 is the first charge in coulombs. Q2 is the second charge in coulombs. To find the direction of the force, however, we use like charges and unlike charges. By the way, this is not the formula on your formula sheet. What did I add on your formula sheet? Find it. What do you notice it's different?
Absolute value.
Absolute value. We have charges that are negative and positive. You're not going to put a negative or a positive sign into the actual equation. Your force will be positive. The negative and the positive tell you the direction. If they're unlike charges, they attract. If they're like charges, they repel. So don't put pluses and minuses into the equations. We decide the direction based on the signs. This also opens up another thing that physicists have wondered for a long time. How many types of charge are there? 2. A negative and a positive. What equation does this look an awful lot alike? You told me. How many types of mass are there? Why aren't there 2? Sure looks like mathematically there should be an anti-gravity mass. There should be a mass that repels, which would, by the way, solve all of our space traveling woes if it was out there, because then you would flick a switch and your spaceship, without burning any fuel, would be... that would violate the law of conservation of energy. Anyways, we've wondered if there is this anti-gravity particle. It looks like mathematically, Sharon, it should show up. Nobel Prize waiting for you if you can find it. Put your pencils down, look up. Example 7 says this: find the direction of the electrical forces on the positive Q charge. So we have a charge positive Q, negative 2Q, negative 2Q, and positive 2Q. What's Q? I don't know, just whatever. So we want to find the direction on this charge right here. We use something that we call, here's your fancy word, the principle of superposition. And what does that mean? It means you only do 2 charges at once. So in your mind, scribble out those 2. Don't do it actually, but I will. What direction is the force on this from that? We're going to use like repel, unlike attract. So what direction is the force on this from that? Let's draw a little arrow pointing that way. Now in your mind, scribble out those ones. What direction is the force on positive Q from this one here? Now in your mind, scribble out those 2. What direction is the force on positive Q from this one here? Alec, can you say it in English? You're pointing, yeah. How would you describe that? Up and left. Sure. Up and left, north and west, yeah, whatever. So let's just, definitely that way, yes? Except, I think since the distance is bigger, I think the force would be weaker, and so I'm going to kind of just do that by doing a shorter arrow. How would I add those three vectors together? Tip to tail. I'll do the easiest ones first. So I'm going to go like that, like that, like that. The resultant is this red line here. I think this charge would ever so slightly move diagonally down, but as it moved closer to this big charge, the force would get bigger and repelling it. Probably you'd find a spot. There's probably a spot probably right about there where the net force is zero, where all of the forces cancel out perfectly. That would be a spot. If this was, for example, some kind of charged substance like a fluid, that would be where that charge would end up in its happy equilibrium place if it was free to move. Of course, these would all be moving around like crazy as well. Okay. In chemistry, who's in chem? Do you talk about Brownian motion at all? Okay. This is part of what's responsible for the fact that on the molecular level, everything is moving around when you zoom. Nothing sits still. This is why if you drop the food coloring into the water, it will slowly spread through the water, even if you don't add any extra energy to it, because the particles themselves are all moving around like crazy because they got charged. Okay. So, to solve a force problem, we're going to express the charge in coulombs. We're going to substitute charges and distance into Coulomb's law to find the force. And we're going to use like repel, unlike attract to figure out the direction. A little technical comment here. If we have unlike charges where one is positive and one is negative, that would technically give us a negative answer. We don't want a negative answer for our force. And so the significance of the negative indicates attraction. So this is why I have put absolute values around your formula sheet. It says add absolute values to your formula sheet right now. For you, I did that this year, I think. Yes? It is on your sheet, so you can scribble that one out. And this is telling me that, good gosh, I may have photocopied my older lesson because I remember deleting this, but I must have deleted this after I photocopied it for you folks. Dumb. How far are we going to get, Mr. Duke? Let's do one more. I'm going to hit pause. No, we're going to hit